Right, okay. Good morning, everybody. I think I'll just make a start. We can treat this as a bit of a recording session, I suppose, more than anything else. But thank you all for coming. This is one of the issues with my kind of late messaging going out, but we'll get there. The main thing that it's recorded so people can go and look at it again. So one of the requirements that you have for the third assignment is actually to work out how much or how you're going to deal with your stormwater, I guess. So my ambition was really to work out how much water we were going to collect, but I think I'll be happy with just figuring out how big the gutters are and the downpipes are going to be for this, because I think it's going to be a bit of a big ask, but we'll see how we go. Okay, so short lecture today on roof drainage, and then after this we might just have a few comments about assignment 2, which we are nearly done with grading, and we'll get that up, we'll post that soon. So really today's lecture is about roof drainage as it pertains to your assignment. So what we want you to do is really to figure out how you are going to get rid of the stormwater from your stadium roof that you're designing. Now, I suppose when we're thinking about roofs, we know plenty of domestic roofs because that's what we live with every day. And in earlier units in this course, undergraduate units in this course nowadays, we do teach about domestic construction, and roof drainage is also part of that. I suppose one of the issues with that is that, in fact, the roofs that we deal with this stadium are much larger than the roofs that we do on the domestic level. So one of our problems is that the main reference for this is something called the Lysart referee, which is on the Moodle, which of course we have to take into consideration that they are trying to sell their products as well as give us good information to use. So when you look at a roof like this, it is unlikely that that any of the standard products will be adequate to drain this kind of roof, because really it's more designed for these kinds of roofs that you see here, domestic tile and steel roofs. So even the one on the bottom, which is what looks like quite a monstrously large house, it will still be okay with many of the domestic products that are provided by Lysart. So when we look at things like this, which is really more the scale of what you're dealing with your assignments, then we start to move away from domestic standard domestic sections in terms of gutters and downpipes and what have you. So what usually happens with these things is that the gutters and downpipes are really calculated from first principles, and then they're prefabricated. So what you can do is a lot of these metal shops you have around the place will have these really long folding machines, and they will fold flat sheets of ColourBond or thin steel into the shape specified. And of course that shape is designed in terms of how it looks, but also how it's going to also for the capacity of water that it's going to take in terms of cross-sectional area. And just as a further demonstration of that, what you can see here on the screen, let me turn off the front lights. What you can see here on the screen is really quite a dramatic demonstration of this difference. So what we have here is the Canberra Centre. So this is actually David Jones right here. And you can see Reed over here. So even when you compare across Kooyong Street from the Canberra Centre buildings to these apartments over here, you can see that you can see the difference in scale. And even further, if you look at all of these houses and duplexes that you get in here in Reed, Fair enough, they're not monstrous houses, but still you can see the difference in the scale of this compared to this. So really what we're dealing with here is quite a different kind of scale. So just a reminder that we can't use domestic rainwater products for what we're dealing with here. So in terms of stormwater services, what's our purpose? Essentially, our purpose is to remove rainwater from our roof, so that it doesn't damage the roof, because of all the extra weight, and also so that the water doesn't get into the people who are sitting below. Okay, so it's quite a simple concept. We've got to get rid of it once it is sitting on the roof. Now, so what I wanted you guys to do was to calculate the gutter sizes and the downpipe sizes. So when we're talking about these kinds of things, really what we're talking about is the cross-sectional area. Okay, so when you cut through the gutter, how much area do you have in there? That actually determines how much water can be taken. Okay, now this very much also ties in with the design of your roof. So essentially we have to remember the universal physical or physics principles that water wants to go downwards, the principles of gravity, so that we have to look at our roof and see where the low points are, and that's where the water wants to gather. And then from those low points, we have to see how we can actually channel the water out or off the roof. Okay, so in many of these cases, if we look at the examples we have, a lot of the roof material itself actually acts as the gutters. So when you've got those kind of folded membrane roofs, it is actually the valleys of those folds that actually act as the gutters and take the water away. So all that water goes to a certain point, and then from there it needs to be channeled off the roof or channeled to a different place and then off the roof. In which point it may be collected or it may just go into the main stormwater. But we won't be looking at that. We really just want to know how it's going to get off the roof without just falling off the edge of the roof. Okay, so I suppose what I'm saying here is you do need to look at your designs to make sure that you know where all the low points are. There may be points in your design where water decides to pool. That's absolutely fine. There's no issue with pooling water on the roof. We just have to design a way to get rid of the water from that pool. Okay, so if you've got an upside down pyramid held up on one column, then obviously what you're going to need is a downpipe that goes through that column so that any water that's collected in there will actually be able to get out. Okay, so what we need to do here, in that example, of course you won't have a gutter, you will just have a downpipe. Okay, so really what we're now going to do is to figure out how to determine those things, because they can be seen in isolation as well. So the information we need before we start this exercise is really the rainfall intensity for the area that we're designing in. So for all of us, it's actually Canberra. So we need to figure out what the rainfall intensity is. So rainfall intensity is measured in millimeters per hour. So those millimeters refer to a rain gauge. Okay, so what a rain gauge is a round cone with something like a 1 meter diameter, which goes down which funnels down to a gauge, which is a smaller piece of glass that is vertical, and which has gradation. So all of these are standardized things, and what we do is we just read off the millimeters down the bottom to see how much rain has come in. And then the roof design and area is what we've looked at, what I've spoken about. So for the purposes of this, of assignment 3, what I'd like you guys to do is just to work out the plan area. okay, rather than the surface area. So of course, with the surface area, you've got to take into account the area of every single different slope, be it curved or flat or sloping or a parabolic, hyperboloid, or what have you. But for the purposes of this exercise, we will just take the plan area of the roof. So what what you're looking down from the top, that area, and I'll explain a bit more about that. The third thing we need to ascertain from the design is really the type of gutter that we're going to have. There's two types of gutters. One is a box gutter, and one is an eaves gutter. Do we know what the difference between the two is? Anyone want to hazard a guess? Okay, no, it must be a bit early in the morning. So essentially what an eaves gutter is that it is a gutter on the very edge of the roof, on the outside edge of the roof, or the inside edge of the roof, and there's no further structure beyond that gutter. Okay, what a box gutter is a gutter at a low point which has the roof draining into it on one side, and on the other side it might have another roof draining into it, or it might actually have a wall or some similar sort of arrangement. So if you think about parapet walls for roofs, where walls come up past the roof and the roof actually comes into the side of the wall, a gutter at the low end of the roof there would be called a box gutter. Now, why we need to do this is because there's different things we have, the different formula we have to look at in terms of box or eave gutters, and then we have to look at also where those things are going to be, where are the sensible places for gutters to be. So we want them to be in the valleys, in the low points, and so on and so forth. We don't want them to affect the way that translucent roofs look, so we got to put them in certain places of transition, and so on and so forth. And then finally, we come to downpipe locations. So what we've got to do here is look for sensible places for which we can put our downpipes, which is really how we get the water from the roof down into the ground, from which you can then go into the stormwater or into tanks or what have you. Okay. Now, there's two references that we've used in the past. The first is the Lysart Referee, the 30th edition, and a copy of this can be found on the Moodle. And the second one, which is really the Australian standard for it, is AS 3500.3 of 2015, which is really stormwater drainage for buildings. Okay. Now we won't be using this for this unit because it is actually really comprehensive and as a consequence quite complicated. So what it does is it takes into account rain direction. So you can imagine that if the rain is coming straight down, as with our situation, that is going to be one thing. But if the rain is coming at a certain angle, then that's going to be a completely different situation, which is why I've specified that the rain is coming straight down vertically and not affected by wind. So if you can imagine a roof that's on a slope of 45 degrees, so in plan, you're going to have one area, but the actual surface area of the 45-degree roof is obviously going to be more, because then you have to look at it at a 45-degree angle. So if you have your rain coming in at 45 degrees, then obviously it's going to have a bigger catchment area, and therefore your gutters and downpipes need to be adjusted to suit. So AS 3500 actually allows for all of this. Yeah, so it's really quite sophisticated. It actually also allows for parapet roofs as well. So on the one hand, you have the catchment of the roof itself, but if you've got rain coming in at an angle, it provides formulae for you to actually work out how much rain is actually collected by the upstands, okay, by the walls that are next to gutters. Quite complicated, so we won't be looking at that for today. This is really more for your information than anything. So we're going to have a little back and forth here between the PowerPoint and the referee, and I'll take you through it step by step. So what we'll do is go to, let me see here, Blindsight referee. Okay, do not open. Okay, so if we go back to this, you can see here that step 1 is to determine the rainfall intensity of the location, which we can see from page 108 of the referee. So if we go here, go down to page 108. Okay, so if we go here, page 108, what we can see is basically the design rainfall intensities. Okay, so the first one, of course, is Canberra, and we can see here that there's 2 columns here. So for overflow of eaves gutters, once in 20 year in millimeters per hour, 137. Okay, and then there's a second column here, which is for overflow of internal box gutters once in 100 years, and there we have to allow for 194 millimeters per hour. So what we can see here is essentially that you've got to that box gutters you need to allow a higher rainfall intensity for box gutters. Mainly because the consequences of box gutters overflowing is much more serious than eaves gutters. So eaves gutters will just overflow to the outside, no big deal. You know, you get a bit of splashing down the bottom, but it's not going to get into the building. Okay, but box gutters may. So you guys, I imagine a lot of it will have to do with box gutters that you're dealing with. The next.
Do they explain the reason why for box gutters they keep it as 100 years and this 20?
Okay, so Swati's question is about the 20 years and the 100 years. So essentially, it's got to do with storms. With eaves gutters, you just have to allow for 1 in a 20-year storm, which will have a maximum rainfall intensity of 137 millimeters per hour, whereas box gutters you need to allow for 1 in a 100-year storm, so something that is not going to happen every day. Although in my experience, I tend to design everything according to the 1 in a 100-year requirement, because it seems that we're getting more and more 1 in a 100-year storms than more often than once in 100 years. So this kind of rainfall intensity we're seeing maybe 2 or 3 times a year. So it's probably a good idea to deal with that, the higher rainfall intensity to start off with. Now, the next step is to calculate the area of the roof catchment of your design that is draining into a gutter. And so I've already spoken about that. So what we'll do is we'll take the area and plan, and you won't have to actually work out the surface area of your thing, of your roof. So the third step then is to calculate the required cross-sectional area of the gutter for the portion of roof draining into it. Now, which is page 100 of the referee. So if we go back to that, go up. So what we see here is the rainfall intensity, which we were going to use. So what was the rainfall intensity that? So 194 was the once in a 100-year rainfall intensity required for box gutters. So we use a 200. Because that's just the closest one, and then we need to then go and look at our roof area. Now remember that this roof area is the catchment area that's draining into one downpipe. Okay, so if your roof area is bigger than that, that's fine. If you can divide it into 200 square meter portions, because you have one downpipe every 200 square meters, then that's probably going to be okay. So let's see. Our structural grid is, what's our structural grid? About sort of 14 or 15 meters or something? 15 meters. So what's the maximum number of seats in a row? Okay, let's say 28 times 600. So that's so it's about sort of I would say it's 18 meters. Okay, so it's 18 meters for your structural grid, and our roof is likely to be something like 27 meters maybe. So 27 times 18, so that's 486. Okay, so that means that you need to have you need to have two downpipes in every structural bay. Okay.
Specify the diameter of the downpipe?
We're getting to that. We're getting to that. So basically, this is right. So it may you will be able to increase the roof area if you use a bigger downpipe. So if we use that, basically from 200 we go across here, and the cross-sectional area required to drain 200 square meter roof is 28,060 millimeters squared. So 28,060. If I just take the square root of that, then we're going to end up with a square section downpipe that is 167 by 167 millimeters. Okay, so that's pretty much how we work it out, and we can make it circular, rectangular, any shape we want, just as long as it ends up as that cross-sectional area. So let's see. So that's. I'm sorry. Let me retract that. That's the cross-sectional area of the gutter that you need. All right. So basically, your gutter is going to have to be 167 by 167, which is not very big, right? It's, you think about if you think about your 300 mil long scale rule, it's only slightly more than half of that. So really, we're not talking about sort of large things. If we double that gutter size, then we can actually take double of the roof catchment area. So if our gutter is 330 by 167, we can then drain a roof area of 400 square meters. Okay, so you can extrapolate these things just by doubling things. Sorry, I did mean to say a gutter, and I was saying downpipe. So sorry for the confusion. So that's step 3, your gutter, and then step 4 is to calculate the required size and number of downpipes required. Okay, so if we go to, I've lost the page number. Where's the page number of this? Is it okay, let me okay, here we go. Downpipe capacity, page 107. So let me just put this in here. Okay, so once we've got our gutter and our roof area, we can then go to the downpipe calculation. So downpipe capacity. Now it tells you here that it should be made from coated steel conforming to AS 1397. Remember that that Lyside is a steel folding company, and they're trying to sell their products. All right, so we're not necessarily locked into that. The main thing here is really this sentence here. So if we have, so basically the cross section of a downpipe from an eaves gutter should be 65 millimeters squared for each square meter of roof area draining to the downpipe, and then they have another requirement here of 95 millimeters squared for the downpipe from an internal box gutter that for each square millimeter of the roof area draining into there. So if we had a roof area of 400 square meters, essentially we take 400 and divide that by 95, and we get basically let me see. Sorry, I've done it wrong again. 400 square meters. So 95 for each square meter. So we have 95 times 400, which gives us 38,000 millimeters squared, which is the cross-sectional area for our downpipe for 400 square meters. Okay, so if we do a square root of that, then we're going to end up with a square downpipe of 194 by 194. Okay, so it's.
But it should be less than half of that of the gutter.
Sorry, what was that?
There's another, like the next portion of that is that the downpipe itself has to be less than half of the gutter to which it drains.
Yes,
Size.
and
I've
I've.
got a 167 gutter square.
Yeah.
It has to be at least.
Yeah.
30, like,
Yes. So, but I mean, the other thing is that generally what you find, I think, is that the box gutter generally ends up being that's pretty easy to conform to. Let me say that, and it's not going to hurt in any case because if the bigger the better, really, when it comes to these kinds of things within reason.
I guess my comment was you can't just have one big 190 square meter downpipe. Like that's like there's center requirements and things.
Well, you can have one big 194 by 194 downpipe for every 400 square meters of roof. Now your roof is going to be more than 400 square meters. Depending on the size of the gutter. Yes. Yes. So essentially, the other thing is that if you have two gutters, if you have two downpipes, then essentially you can halve the cross-sectional area of each downpipe as well.
Surely then there's a center requirement as well.
The center requirement is really got to do with where you can get it down to the ground. Okay, so.
Surely there's I don't know, with residential rainfall catchment, every 12 meters you need to have a downpipe, and it needs to catch 52 square meters of roof per downpipe. There's no stress on that downpipe.
That's right, but with domestic situations, you're also using standard downpipes and standard gutters. Yeah, so when you're designing it yourself, it really frees up a lot of stuff. So all those rule of thumb type things for domestic things are geared towards domestic rainwater products, right? When you're designing it from scratch, if you follow these principles, then you should be fine. So basically, if you had a 400 square meter roof, then you can have one downpipe of this size and a gutter of a certain size as well, which you calculate and also for and conform to this principle, whichever is larger. So what there are many. It's surprising how few you need. There was actually a company that was doing siphonic downpipes. And what they could achieve with that kind of downpipe was really to have a roof as big as this, as big as the one this warehouse here on the top, all draining into one downpipe. Okay, and that's because what they did was they had a specific kind of box gutter. Which then forced the water into a spiral, and because the water was going in a certain direction, pretty much like a toilet, right? Because it was sort of twisting in a certain direction, it sucked all the water out of it. Yeah, so you can actually, it's remarkable how little you need. Really, what you have to remember is that a lot of the rules of thumb that you find on the websites of roof manufacturers has got to do with risk. You know, they got to tell you what to do so that it doesn't come back to bite them. So it's not actually a requirement. Rather, it's not actually calculated to the standards. It is more than what's required by the standards, so that they don't get into trouble, because they want to be helpful and recommend numbers of downpipe sizes, gutter sizes, but they also have to take into account that the people who are reading these things are not necessarily trained people. But those same people might come back and sue them if it doesn't work regardless as to the kind of disclaimers that they put up. Swati, did you have a question?
Yeah. So that particular gutter and downpipe, does it work on the mechanical system? Probably no.
No. What the question was about the siphonic system. It's not a mechanical thing. It actually, just by the shape of the entry into the downpipe from the box gutter, it forces the water into a certain pattern, which then causes makes a bit of a whirlpool and sucks everything down much faster than. There is a bit of a funnel happening, but it's got to do with how it goes into that funnel. Because once it's set on a certain path, then it just drags everything through. It doesn't need actually to be very much of a funnel. You think about a funnel, all water goes straight down the sides. It's actually about directing water into that funnel so it spirals down the thing. Yeah. Yes, it's called a siphonic system, and of course the most common use of siphonic systems is actually in American toilets. If you ever travel to Southeast Asia or to Japan or to America, they love having these toilets with like a swimming pool in it, like lots of water in it, and what happens is that when you push the flush, it actually shoots a jet of water sideways. There's always this kind of opening in the bottom of it, or another opening in the bottom of it, and it shoots a jet sideways, which creates a whirlpool. And then basically that whirlpool then creates suction, which pushes everything out the outlet of the toilet. Of course, the problem there is that there's a lot of splashing, if I might say so. So if you're having a number two, what happens is that your bum gets wet, which I think is kind of unpleasant, which is why I don't like them. Now, I'm sorry to have to go into the gory details, but as architects, we need to know this kind of thing. Yeah. Generally, they look like very modernistic fighter jet type, cockpit type things. So people like them because of the way that they look. But in terms of how they work, that's a completely different matter. We hardly ever see it in Australia because in Australia, dual flush is required by law, and the siphonic systems use a lot of water, so you can't do a kind of half flush or with a siphonic toilet. But I digress. Going back to this, that was step 4 in terms of calculating downpipes, and then step 5 is really to design the gutters and the downpipes. Right. So in that that's where we have to look at that, what you want, whether it wants to be square, rectangular, or round, and really it's got very much to do with how it's actually incorporated into your structure as well. Because the difference between the house and the stadium is that generally with the house you've got lots of wall to pull downpipes down against, and it doesn't really matter where you put it. But with stadiums you have sort of big glass walls and roofs and things, and you want it to be integrated into the structural and cladding systems so that it looks considered. It doesn't mean that you can't see it. It just means that you got to know where it's going, and you got to know whether you're happy with how it looks on the elevation or not. Any questions?
Overflow. Are there any spigot requirements or some kind of an overflow point?
Yes. So generally, with generally you have between the downpipe and the gutter, or between the gutter and the downpipe, you generally do a sump, which is essentially a deeper portion of the gutter, where water can collect if necessary, and then that sump generally has an overflow, which then goes to the outside.
I was thinking more in the roof realm up near the gutter. Surely there's an overflow point that needs to be included.
No.
Especially if it's sitting behind a wall or.
Well, put it this way: if you design I suppose it comes back to what's going to cause a blockage. Yeah. So you only need an overflow if there's going to be a blockage, because you can essentially design the system where the water will always be able to get away, because you are like we're doing, over designing the size of the gutter, making the gutter bigger according to the worst case rainfall that we get. Yeah. So if you design it according to the worst case rainfall that we are getting right now, which is what we used to get once in 100 years, then you're not going to have a problem unless you have a football sticking into your downpipe. Okay, which is what generally happens with domestic situations, is you get leaves and tennis balls and all of those things. So those are maintenance issues, because essentially, if you had a lot of rain, your overflow is the same as it's not going to help you that much if your downpipe is completely blocked, because it will just back up and the whole thing will fill up, and the overflow won't be able to get rid of enough water for it to have backwash back into the house. So domestic situation is different again. Domestic situation, generally box gutters do hit the outside of the buildings, and then you have a rainwater head in there, which is a tank that collects all the water, and then it overflows. So what we're dealing with here is a much bigger scale thing, and really where if you've got valley gutters which are going from the front to the back, and the low point is at the back, then you would have some sort of overflow system there, or if it then goes into another box gutter which takes it to the edge, then at the edge you will have some sort of overflow type system. But generally, in these kinds of big roofs, because everything is so big and you're unlikely to have leaves getting in there, you have commercial maintenance regimes and so on and so forth. This kind of stuff shouldn't happen unless we get unless we get more rain than has ever been recorded in the past. And now we're in a new rain pattern, so everybody is really going for much worse scenarios. If you're really worried about it, then use the rainfall intensity from Cairns, which is what I tend to do when I design box gutters. And the other thing is, it comes down to function, right? When I was talking before, we ended up with a box gutter that was like 167 by 167. That's for an area of roof of 400. That's a really convenient size to get your foot stuck in. So what I'd be much happier with is to actually make the box gutter wide enough so that one can actually walk in it. Yeah. So you make it 600 wide, and then then it can be a lot shallower. If you don't need it to be a lot shallower, you just keep the standard depth and just make it wider. So for you guys, what you need to demonstrate to me is what the minimum size is and what you've ended up designing, because the other factor is how it's going to be used up on the roof. And this comes from this comes from my own experience of putting my foot into a valley gutter on a roof, on a steel roof, and getting my foot stuck in the damn thing, because you've got two bits of tin coming in like this. Foot goes into this tiny gap, and then it wasn't so much my leg that got stuck; it was my shoe that got stuck in there. So in the end, I managed to get my foot out of my shoe and then turn my shoe sideways and get it out. But it's so dumb, right? Why don't you just make it sort of 100 mil wider? Then this wouldn't happen. you know. Anyway, we can't all be. Some of us are a little more clumsy than others. Let me say that.
What were you doing on the roof?
Okay, so what was I doing on the roof? I needed to get up on the roof to see how it was actually arranged, and to check to see to check to see the condition of the roof and the gutters. Also, making it bigger makes it easier to look into. And of course, nowadays we have drones for all of these things, so you don't actually have to climb up onto the roof, which is a much sort of safer situation. Okay, I was actually going to calculate you out an example, but I think we've already done that, so we'll move on from that. Are there any questions? No? Okay, so for those of you who missed the first bit of it, that's fine. We've recorded it, so I'm going to upload it onto YouTube. Because I think the problem with the Echo 360 is it only records from half past to quarter past, so it only does 45 minutes, and so you always get a bit chopped off in the back. Now, while we're here, we are in the process of well, we've marked, Swati and I have marked all of your assignments from assignment 2. So what we now got to do is we have to moderate against each other to make sure that that the grading is consistent between the two of us. So just some comments from me with regards to the ones that I marked. 1,500 words is really not a lot of words. So I think this kind of report, if you actually start from the point of view of answering all the questions from the list that was required, like in terms of the grandstand construction and materials, the roof construction materials, how advanced it was, how conventional it was, and so on and so forth. I think that was if once you covered all of those things, if you covered, no matter how briefly you covered those things, then you got a credit. Okay, this is of course considering that it was correct to start off with. Okay, and there was some really good. By and large, they were pretty good. By and large, they were really good reports because you guys demonstrated that basically you looked at the right kind of references. There was a correlation between the quality of the references and the quality of the report, and also the number of quality references and the quality of the report. Okay, so that was, but that's pretty straightforward. I'm sure you all know that anyway. What I would say is that the reason why we called it a report rather than an essay is so you didn't have to do all that kind of fluffy stuff which referred to contextualize it within sort of contemporary architectural theory and so on and so forth. All right, so as you know, as far as I was concerned, that was all interesting to me, but didn't actually add to the grade. It was kind of irrelevant, but it was fine for it to be there, except that the number of words you use discussing Marxist theory. Well, Marxist theory is not a good example because that might actually be relevant. If the amount of words you use to discuss Foucauldian theory, I didn't actually get any of those, by the way, could better be used to actually talk about the examples of the things themselves. Now, the second thing is that it came down to the description and analysis of systems. I think at this stage, there needed to be a bit more description of how the systems worked. So if it was conventional, that's fine. You tell me how it's conventional, but how do those conventional systems actually work? So there were a couple where I was having trouble I understood what the system was, but I didn't understand how it worked in that particular instance. Yeah, so again, it's always good to just have brief descriptions of all of these things. Swati, do you have anything to add?
Yeah, and the ones I marked, so what I was looking at was
what I was looking at was how you have answered the questions, but more importantly, what is your reflection about it? How will you take it further? How will it help you in resolving your project? It might be an intention in terms of the way you've approached the analysis, or it might be that in conclusion you say there are certain strategies which I carry forward, which I think it is really important and very good of John to say it as a report and not an essay, because if you really look into how architectural practices are going in our contemporary world, architectural practices do reporting, and they are absolutely analytical reporting. And I think I give you full credit, John, for calling it analysis and calling it an analytical report, because it has a certain language that you need to develop. And John is right. You take a theoretical framework, but then you don't uh, write a report based just on a theoretical framework. You have to communicate that you've understood those ideas, more importantly, how they are applied. So that was something that I was looking at, and how you connect visual references to your textual description. I think there is a disconnection that I'm seeing. There are images, but you need to highlight what you are talking about. That cross-referencing is something quite a few were missing, but they were there. So these are things I think is up to us to tell you. So that is something we will emphasize in our feedback as well. Otherwise, I think most of you did quite well. I enjoyed reading all those that I read.
Thanks, Swati. I think it was a good length because it wasn't too bad to write, right? Yeah. Look, I think also one of the things that because it is an analytical thing, you're also analyzing the question in many ways, because it was complicated because some of the examples that you guys chose were both conventional and advanced at the same time. And of course we all know of the examples of the older examples, which are actually more advanced than the newer examples for whatever reason. So I think a questioning of the question was very much welcome as well. Just to say basically that there's no one clear way of doing it. So I think, and it was also good to see all the images that you guys had included, of the ones that I didn't know very well, and there were some really amazing things in there, and of course, I think that what you can do with your own design approaches is really to adopt those systems and fix up their problems. Fix up their problems. Like the most ridiculous and amazing in the same note. One was the Braga Stadium. Who did that one? The Braga Stadium, because it had this really amazing cable roof that had these concrete slabs over the top of the cables, which was a really amazing idea. But then it had these 16, I think. 16 pylons that were each 1 meter thick, that were essentially cantilevered out of the ground, which also held the seats, but which could have been easily overcome with having a column and a cable stay back anchored into the ground, right? So it is these kinds of things, when we look at systems and there's different ways of dealing with the problems that we see in these designs. It's absolutely fine to fix up those designs when we come to our own projects. Any questions? Sorry, I can't. Very good, very good. Okay, so let's call it a day for the lecture. We'll have a quick coffee pit stop, and then we'll adjourn to the tute room. Thanks, everybody.
Thanks, John.
Thank you.
Giving design.